complicated circuit with a number of capacitors in one battery, and you know all the information about the circuit, and you're told to go through and find the charge on each capacitor. So we're going to go through and do this, and our procedure is going to be like this. We're going to first of all find the equivalent capacitance of the whole system, which is a common problem that you might be asked just by itself. And then we're going to go through and use our capacitor equations to find the charge and the potential difference for all different parts of the circuit. And so with more complicated circuits like this, there's a little routine. It's kind of like solving a little puzzle we can go through to solve for all this. And here's our capacitance style equation. So the first thing we want to do is go through and reduce this circuit to its equivalent capacitance. And the way we do that is using our rules for series and parallel. And so the first thing we have to do is understand which ones are in series or parallel. This is not always easy. It can be tricky, especially when you're starting out. So here, look at our circuit and try to figure out which two are either in series or parallel. Go ahead and pause it, and we'll talk about it in a second. Okay, so hopefully you got that the answer here is C. That C3 and C4. And so there's different ways to think about this. The way I like to think about this is if you look here, okay, when two things are in parallel, you can go from the bottom of them to the bottom of them without touching anything else. So I did that. You can also go from the top to the top without touching anything else. Okay, so those are in parallel. I can go top to top and bottom to bottom. Now a lot of people look at C1 and C2 and think they're in parallel. Well, if you look at those, I can go from the top to the top, no problem. However, if I go from bottom, I go over here, I get bunched up and get run into stuff. Okay, so I can't do it. So the only answer here is C3 and C4. Sometimes people get mixed up because sometimes capacitors aren't either. C1 and C2 aren't in parallel, they're not in series, they're just neither. So series and parallel is kind of a special thing, and so sometimes it just doesn't happen. But the way we do this then is that we start with that piece and we work down and reduce the capacitors. So we know that the 3 and the 4, those guys are in parallel, so we use our parallel equation, which is like this. So C equivalent equals, you just add them up. When they're in parallel, it's the easier equation of the two. You just literally add them up. And so here's 3 plus 4, and so we end up with 7 microfarads. And so what I do is I draw a picture for each step of the way. So here I've literally just replaced the 3 and the 4 with one that's 7. And so now you look at it, and it's the 2 and the 7 are now the ones we're going to be interested in, all right? And they're in series, all right? If I go through the 2, I have to go through the 7. There's no alternate route. So these are in series. And now this is the one that's a little bit more of a complicated equation. So to find the equivalent capacitance here would be 1 over 2 microfarads, and then plus 1 over 7 microfarads. All right, and you go through and do this math, and you find out that the answer here is 1.6 microfarads. So make sure that this math makes sense to you. Okay, we did an example like this in the pre-lecture video, but make sure this makes sense. It's a little bit complicated, and it might be your first time going through, it might be kind of tricky. But now we're almost home free. So now you can notice that the 1 and the 1.56 are parallel, right? If I go from here to here, I can go bottom to bottom and top to top, no problem. All right, so you add these together, that's not too bad, and you end up with your equivalent capacitance. So basically all those 4 capacitors initially can be replaced with one capacitor that's 2.56 microfarads. So that's our first step, and sometimes the problem will just ask for that. So that's important to be able to do that. And like I said, it's like a little Sudoku puzzle or something. You work through and get the answer at the end. Now, for the second part, I like to make a little table. So here's a table. We're going to fill out this whole table for all the capacitors. So we're going to find the capacitance, we're going to find the charge, and then the potential difference. And we're going to go through and do that. All right, and so we start with our ending point. Now, I like to call this the simplest circuit in the world. It's one battery and one circuit element. All right, and so you start here, and you know that your circuit element has to have the voltage of the 10 volts because of Kirchhoff's law, right? And so there has to be a voltage drop of 10 volts on this capacitor. So I put in 2 pieces of my chart. So generally, as you work backwards through the circuit, you'll be able to get 2 pieces of the chart pretty easily. Then you got to go to the circuit or to your equations for the other part. And so that's what we're going to do here. So I got the capacitance and the voltage, and so my last thing I want to find is the charge. And so we go to our capacitor equation that looks like this. And so since I want to solve for the charge, I just do like this, and I just plug in my numbers. I got my two numbers, I can plug them in. So it's 2.56 microfarads for the capacitor, and then times 10 volts. So I basically just multiply this by 10. And so here's kind of a tricky thing. When you have that micro, okay, we know that farads times volts is coulombs. And so here I just sort of take the micro along for the ride. So it's in microcoulombs that we're measuring our charge. And so I fill in the third part of the chart. So now I know everything there is to know about that capacitor. And so what we do is what I like to call unfolding the capacitors. Now I don't know if anyone else calls it this, but that's what I like to call it. So we unfold the 2.56 into its constituents, which were the 1 and the 1.56. Here's where it's really nice to draw your pictures along the way. One thing is, once you get good at this, you can sort of do the equivalent capacitance part in your head sometimes. If you don't have your pictures, it's really hard to do this unfolding, this backtracking. All right, but here we have the 1 and the 1.56, and so I put those into my chart. I want to find out everything there is to know about those. And so here's the piece of information that you need to be able to do this, and that is that we know there's something about parallel and series resistors. So here's parallel. We know that when capacitors, when two capacitors are in parallel, we know that the voltage, okay, the potential difference across them is the same. Okay, so the delta V1 is equal to the delta V2. When two capacitors are in series, all right, we know that the charge on them is the same. So basically, every time we unfold to two different capacitors, we know that one piece of information has to be the same as the one that it unfolded from. So these are parallel, so that means the voltage has to be the same. So two pieces of our chart are super easy to fill out. Okay, it's 10 and the 10 because that's what that was for the 2.56. And then for our last step, okay, again, we go back to our capacitor equation, and now we're solving for, again, the charge. And so we do this for our next two guys, and it's just sort of the same sort of idea. And so I'll just do it for one of them. So the 1.56 microfarads times, again, we know the voltage is 10 volts, and so I get 15.6 microfarads. So I get that, and then if you do it for the 1 microfarad, you get 10. Now one thing that's really important is you can check yourself here. If you look at these two charges, so the charges aren't the same, but what happens is if I add up the two charges, it should equal the charge that was on the original one. Okay, so you can always go through and check yourself, make sure you didn't make a mistake, which is nice. So now we've got this part. Okay, and so that's just where we just sort of left off for. So we got that, and now we got this guy, and we want to unfold the 1.56 into its constituent pieces, which are the 2 and the 7. Now, in this case, these are in series. All right, so I put those two pieces in my chart. So since they're in series, what stays the same is the charge. And so the 15.6 was the charge on the 1.56 microfarad, right? So I literally just took this guy over here and just transferred it over to here. And now we take our same equation, all right, this guy, but now I'm looking to find for the voltage and not for the charge. So the way this would work is the voltage is going to equal the charge divided by the capacitance. So we just do both of these now. So again, I found two pieces of information right away, and the third one I got to use my equation for. And so I know that the charge is 15.6 microcoulombs, and so let's do the 7 one first. So it's 7 microfarads. And when I plug that in for that one, I get that it's 2.2 volts. All right, and if I do for the other guy, it's just the same equation. So the 15.6 microcoulombs over the 2 microfarads. And what's nice is what's happening here is the micro part is just going to cancel out, so you can kind of just even forget about it. 7.8 volts. So I get those two. So again, two pieces of information I had to solve with the equation. Now here's another nice little trick to check yourself, is that the voltage drops across these two capacitors should equal the voltage drop of the one from before. So 2.2 plus 7.8 equals this 10. All right? And so that's another way to check yourself. So now we're almost home free. We got one more unfolding to do. So we unfold parallel style into the 3 and the 4. So I put those on my chart, and of course we know that parallel means that the voltage drops are the same. And so then what this becomes is now just the final thing to find the charge. Is just the charge is equal to C times V. And we just do what we've been doing the whole time. So 3 microfarads for that guy. And now the voltage here is the 2.2. Okay, so I do that. And for the 3, I get 6.6 microcoulombs. You do the same thing for the 4, you should get 8.8. And then one final thing here is that our Q total now for these two should add up. And so let's look at it. So I get 6.8, 6.6 plus 8.8. Now if I add this up, it doesn't quite come out to be 15.6. Okay, so that's something that you got to be careful about. Now, why is the reason for that? Well, it's basically because I just rounded kind of weird, okay, which is hard to do. It's hard to round up, but I get 15.4 microcoulombs, so I get that these two guys add up to be pretty close to this one. Okay, not exact, but that's just a rounding problem. Okay, thanks.